Okay, we were discussing about the wavelets in the last class. So we have seen that how you can decompose a function in terms of on the wavelets. Okay, so we have started from some basic notations in signal processing, which says that any function f of t, it may be decomposed as a linear combination of some basis functions. Okay, and if these basis functions they are orthogonal, in that case these expansion coefficients ak they can be computed using the inner product of the function with the basis function. Okay, this is general theory in signal processing, and we have given a example that how we use this expansion in Fourier series, where a function which is periodic, it can be decomposed in the form of complex exponentials only. Okay, and since e raised power j omega naught kt for different integer values of k, this form a orthogonal set. So this ak, which is the Fourier series coefficient in this case, it can be obtained using the inner product of the function with this basis function. So that was integration for one time period f of t e raised power minus j omega naught kt dt. Okay, so and then we have extended this equation to wavelets, where we decompose a function f of t in terms of wavelets. So in that case it is a two parameter system, jk, so a jk psi of jk t. Okay, so where your Fourier series is, it maps a one-dimensional function f of t into a series of coefficients ak. This is done by the Fourier series. The discrete wavelet transform is, you can say, the counterpart of Fourier series, where it maps a one-dimensional function to a set of coefficients with two indexes j and k. Okay, and again, if these basis functions, which are called basically the wavelets, if they are orthogonal, these coefficients a, j, k, they can be again be computed from the inner product of the function with the basis function. Okay, and these coefficients we call them as discrete wavelet transform of this function ft. Okay, so and then further we have seen that this psi jkt, it is obtained from a single function psi t using scaling and translation. Okay, so you have one function psi t, which is the mother wavelet, then you translate it and you scale it. Okay, so j stands for your scaling, because if you increase j, you are basically compressing the signal, and k is for shifting or translation. So if you change k, it is shifted in time along the time axis. Okay, so any signal, it can be then expressed as a linear combination of these scaled and translated wavelets, which are called as the basis functions in this case. And these coefficients, expansion coefficients, they becomes the discrete wavelet transform of the function. Okay, and then we have seen that why wavelets they are effective, because in case of Fourier analysis, the basis functions are fixed, they are complex exponentials, or they are sine and cosine terms. Okay, so Fourier analysis, it is useful for analysis of stationary signals, where you assume that the statistics of the signals, they do not vary with time. But if you have a non-stationary or a transient signal, so for that case, wavelets, they are well suited. Okay, because the wavelets, they are not smooth like the sine and cosine function. So you have a family of wavelets, you can choose anyone from that family to decompose the signal in terms of wavelets. And another important characteristic that we have discussed, that for most of the cases, if you decompose the signal in terms of this series, so these wavelet coefficients A, J, K, they basically, the size of the coefficients, it decreases as you change J and K, or you can say that most of the coefficients, their values is almost equal to 0. So that is how these are basically used for compression and also for denoising. Okay, the second example you have taken, that if a function is noisy, so if you decompose it in terms of wavelets, so you find its wavelet transform dWt, you get some coefficients A, J, K. So the noisy part will be captured by few coefficients in the wavelet domain. So if you discard those coefficients and you reconstruct the signal using the other coefficients, your signal will be noise free. Okay. And then you have, so Fourier series is very much analogous to your dWt. Okay, so because we have function which is mapped to a series of coefficients in the Fourier series, so a function which is mapped to a series of coefficients, two-dimensional parameters in case of dWt. Okay, so this you must say that, okay, if it is Fourier series, this must be a wavelet series, but anyhow, that is not the convention. We call it as a discrete wavelet transform. Okay, and if somehow, if your function is not in continuous, if it is discrete function f of n, okay, and you again decompose this function in the form of a series, so you get a transform which is equivalent to DFT in the frequency domain. Okay, in the DFT, what we do, we have function f of n, it is mapped to another sequence x of k. Okay, so discrete time sequence here, you have a discrete time sequence here. Okay, so if you take a function of n, which is a discrete signal, then its DFT is also discrete samples, so x0, x1, x2. Okay, so analogous to that, in case of wavelets, if you have to decompose a function which is discrete in nature, so the transform that we use, it is called as discrete time wavelet transform. Okay, and similarly, then we have continuous wavelet transform also here, CWT, which is used to express a function in the form of continuous variables, not discrete. Okay, and it is very much similar to your Fourier transform. So if you have f of t function which is not periodic in general, so if you find its Fourier transform, you get x of omega. Okay, now this x omega is a continuous function of frequency. Okay, which we call as Fourier integral basically. So x omega is basically integral xt e raised to power minus j omega t dt. Okay, so Fourier series is used when you have a signal which is periodic, so it maps this function into a series of coefficients. If the signal itself is discrete in nature, so we can find its discrete Fourier transform, which is basically itself obtained by the sampling of dTFT. So you have discrete time Fourier transform first, and then you sample it, it becomes DFT. Okay, and if you have a aperiodic function f of t, so if you want to convert this into the frequency domain, you can find its Fourier integral or Fourier transform. So it is a continuous function of frequency. Similarly, if you want the wavelet transform to be a function of continuous parameters, the translation and the scale, if they are continuous, okay, not discretized, we get continuous wavelet transform. Okay, So continuous Wavelet transform of a function, it is now a function of again two variables tau and s, which is given by integration of 1 by under root s f of t psi of t minus tau by s dt. Okay, this is defined as continuous Wavelet transform, and this is very much similar to your Fourier transform or Fourier integral. Okay, the only difference in this case is that your f of t is converted to x of omega, so time is converted to frequency. Okay, in this case your function f of t is converted to, when you have continuous Wavelet transform, so you have two parameters. It is a function of tau and a function of s. So tau is your translation, or we call it as dilation parameter, time shifting, and s is your scale. Okay, again psi t, so psi t is your mother wavelet. So from psi t you basically generate a family of wavelets psi tau s, which is psi t minus tau by s. Okay, now tau and s, in this case your tau and s, they belongs to real numbers because they are continuous. Okay, so again t minus tau means it is shifted in time, and t by s is scaled. Okay, let us see how it, what actually it is. Let me first give you an example about what actually the Fourier transform does, and then we will compare how it is equivalent to the Wavelet transform. What we do in the Fourier, you have a function f of t, you multiply it with the complex exponential, and then you integrate for the entire time period. We get Fourier transform. Okay, so basically what we are doing, you are multiplying a function with a template, we call it as a template or a basis function. So now omega is continuous. Okay, so omega can take any value of frequency, and e raised to power minus j omega t is multiplied with the function, and then it is integrated for the entire time period. You get some value here x omega. Okay, so corresponding to particular any omega, suppose it is omega naught, so you get x omega naught, which is integration of this function with the complex exponential like this. Okay, so what it means, what this Fourier transform gives you at omega naught is basically it finds the degree of similarity between this function f of t and a template. Okay, because when you multiply them together and you integrate them, so you are getting a degree of correlation or a degree of similarity between the function and the template. Okay, or in general you can say that since e raised to power j omega t, it consists of cos omega naught t and j sine omega naught t. So in the Fourier transform, we are basically comparing a function with sine and cosine functions, okay, for different values of frequency which are continuous. So for each frequency, you are multiplying the function with the sine and cosine function, and then you are integrating it. You are seeing what is my correlation. That is given by the Fourier transform. It is a degree of similarity, nothing else. Okay. Let us suppose that if you take a signal in time of t, I take a signal like this. Okay, and if you want to find its Fourier transform, okay, so what basically you are doing, you are generating a set of functions here from this template e raised to power j omega naught t, which will be basically a sine function, another will be a cosine function. Okay, so there is some phase shift, nothing else, right? And for a particular value of omega naught, or for a particular frequency of sine or the cosine, you are multiplying now this template with this entire function. Okay, so for any particular value of omega naught, suppose that this is my function, so I am choosing a sine function with some frequency, and I'm multiplying them together and integrating them for the entire time period. You get some value that is x omega naught at that particular frequency. Okay, in one case you can take sine, in the other case you can take cosine function, and then this function will be same for the same function. What you are doing, you are changing the frequency. So if you change the frequency, you will get a different function. Maybe you're taking a high frequency signal, your omega naught is changed. So here omega naught is different, here omega naught is different. Okay, so the basic idea behind the Fourier transform is that you are basically comparing the signal with different frequencies, and where the signal matches with a particular sine or cosine functions, so at that point this x omega naught, it will give a peak value. So we say, okay, that frequency is present in the signal, right? Suppose for this signal, if I find its Fourier transform, so on this axis now have frequency x of f. Okay, so omega you can write in terms of f as omega is equal to 2 pi f. This is in radians per second, this is cycles per second hertz. Okay, let us suppose if you find the Fourier transform for this signal and get a spectrum like this, maybe. Okay, so we have some frequency here where you are getting peaks. Okay, it means these three frequencies, they are the dominating frequency components in the signal, or you can say that this signal, time domain signal, is basically composed of these three frequencies. So this may be f1, f2 and f3. So other frequency components are also present, but their contribution or their energy is very, amplitude is very less. Okay, this is what is frequency domain representation of a signal, and this is how basically you interpret the Fourier transform. Okay, and the same thing in the Fourier series also. If you decompose the signal in terms of Fourier series, if it is periodic, okay, so you have written a series like this, a raised to power j omega naught kt. So you have these Fourier series coefficients. They again give you nothing but the degree of similarity between the function and this sine and cosine function. So again, finding the product of this function with a basis function, inner product, which is basically the degree of similarity between these two functions. Okay, so the higher value of ak, it means that frequency is present because that is correlated to the signal. So that frequency component is more dominating, or it is present in the signal. If for some value of k you are getting ak 0, it means that frequency is not present in the signal. Okay, so these coefficients, they give a frequency domain representation. Okay, but one limitation, now say this signal, if you take the Fourier transform of this, you get suppose like this. So what you see on average, that okay, these are the frequencies which are present in the signal. Okay, but since you are integrating this time from minus to plus infinity, so you get a average frequency information. Okay, or you can say that from this picture, from this spectrum, you can just tell, okay, that these are the frequencies which are present in the signal, but whether they are present for the entire time duration or they are present at some specific intervals, so that you cannot get. Okay, so it means that Fourier transform is used if you have, okay, stationary signal, that we assume that all the frequencies, they are present for all time intervals, then it is a very well suited mathematical tool. If the signal itself is non-stationary or transient, in which the frequency of the signal that varies with time, So for that case, you may get the frequency information, but if you want to get the time and the frequency information simultaneously, that cannot be achieved. Okay. So for that, you can use wavelet analysis. Okay. Or in fact, Fourier transform, ahead of this, we use short time Fourier transform. So short time Fourier transform is a window transform. Okay, in which you analyze the signals in different segments. So we have window function. You multiply this function with the window function, and then you take its Fourier transform. Then you slide this window to the next position. Again, take Fourier transform of this segment, then this segment, and so on. Okay, so somehow you get time and the frequency information using this, that which frequencies are present at which time. Okay, now if you compare this to the wavelet transform, Fourier transform, the wavelet transform, or CWT I am discussing, continuous wavelet transform. So continuous wavelet transform, we have seen that CWT of a signal, which is a function of now two parameters. You have function f of t, you multiply it with a template and you integrate it. Okay, and this psi tau minus ts, you can write it as psi tau s of t, which is generated from psi t using this transformation. Or you can also write here under root s, which I have written here. So 1 by under root s is again just used to maintain the energy of the signal. Okay, it means if psi t, if you see energy of this function psi t is E, so what will be the energy of this function psi tau s t? It will be integration of 1 by under root s square. If you take square of this function, you will get s, and then psi t minus tau by s dt. Okay, so again, if you replace here t minus tau by s with some other variable, suppose p, so you will get dt as sp. Okay, and this will become now integration of 1 by s, and this is also square here. You will get psi of p square into dp to sp s into dp, sorry, here. Okay, so this s get cancelled, you will get again equal to E. Okay, so this is 1 by root s is factor which is used to maintain the energy of the wavelet at every scale. Okay, now how you interpret this equation, or see how you generate this family of wavelets from a single wavelet. You have psi of t minus tau by s 1 by under root s, or we sometimes use here star conjugate if the function is complex, otherwise star has no meaning. Now psi t minus tau by s, okay, forget the scaling factor of 1 by root s. How you can get this function from psi t? So you can, what you do, if you have function psi t, which is the wavelet function, which is a small wave of finite duration basically. Okay, so if you first translate it, you will get psi of t minus tau, that is shift. Okay, so if tau is positive, so psi minus t minus tau is basically shifted to the right by tau units, and then you scale it by 1 by s. Okay, so it's tau. Now when you scale it, your t will become t by s, so it will become psi of t by s minus tau, or you can say it is becomes psi of t minus s tau by s. Okay, so if you first shift by tau and then you scale by 1 by s, the function that you'll get is psi of t minus s tau by s. This is not this function. Okay, otherwise if I first scale it, if I first perform the scaling operation, it will become psi of tau by s, and then you shift it. You will now, in the shifting, your tau t will change to tau only. This 1 by s factor will remain as it is. Okay, so generating this function psi of t minus tau by s from psi t means you first scale it by s and then you shift it by tau. Okay, now scale it by s. Since scale is in the denominator, it is going to make a different impact. Suppose you have a wavelet function like this. Okay, let us suppose this is my psi t, and I want to generate psi tau t minus tau by s. Let us suppose I want to generate psi of t minus 1 by 2, where tau is 1, scale is s is 2. So what you do, you first scale it by 2, so it becomes psi of t by tau, t by 2. Now psi of t by 2, if you take psi of t by 2, how it is related to psi of t? It is basically expanded by a factor of 2. Okay, its time duration will become double. So it will become like this. Perhaps. Okay. So this will become psi tau by psi t by 2, and then you shift it by 1. So if you suppose, say it is 0 to 1, it will go from 0 to 2. Okay, and then you shift it by 1 to the right, so you'll get a function like this. Okay, so it will start from 1 and end at 3. Okay, so it means since scale is in the denominator, so increasing the scale means you are basically decreasing the frequency. You are stretching the signal. Okay, if you stretch the signal, its frequency will become, if you stretch it by a factor of 2, its frequency will become half. Okay, so if you decrease scale, you increase the frequency of the wavelet, isn't it? So you have to scale it by some factor, then you have to shift it. So if my s is suppose 1 by 2, in that case it will become psi of 2t. In that case, if I take psi of t by s, and if I take s as 1 by 2, suppose it will become then psi of 2t. So it will be now compressed in that case by factor of 2. So its time duration will become half. Okay, the frequency will become double. Scale is half, frequency is double in that case. So decreasing scale means increasing frequency, increasing scale means decreasing frequency. Okay, so generally in wavelets we do not talk about the time frequency, we talk about time and scale. Okay, and scale is the inverse of the frequency that we have just seen. So you have now this wavelet, continuous wavelet transform as a function of two parameters, tau and s, which is given by 1 by under root of s, integration of this function f of t with psi of t minus tau by s dt. Okay, and you see how you compare this with the wavelet transform, with the Fourier transform. Okay, if you compare this with the Fourier integral and the CWT, so in the Fourier transform, what we have done, that okay, you have a signal. Let us suppose you have a function f of t for which you want to compute the Fourier transform. So you choose a template which is e raised to power j omega naught t, or in fact which is basically two functions, one is sine function, one is cosine function. So you multiply this function with the sine and cosines and you integrate it, so you get some values which we call as the Fourier transform x of omega, or for any particular frequency it is omega naught. Now in the wavelet transform you are using the same operation. The difference is that in place of using the sine and the cosine functions, you are using the wavelet for matching. So if you take any transient signal or any function f of t, again here, which may be periodic, it may not be periodic. Okay. So how you find its continuous wavelet transform? You first choose a mother wavelet psi t. Let us suppose this is my mother wavelet psi t. Okay. And then what you do, if you first take s, if you do not change the scale, s is equal to 1, and you just change the tau here, psi of t minus tau. Okay. So you're basically shifting this mother wavelet along the time axis, and then multiply the function and then integrate. You will get, so for one value of tau and for one value of s, you will get one value. Okay. And then if you scale it, suppose you scale it, it becomes psi of t by s. So you have chosen some scale s, okay, which is a real value. So you are basically, if s is greater than 1, you are stretching it. If s is less than, we are compressing it. Okay. And then if you shift it after scaling, it will become psi of t minus tau by s. So you get a function sometimes here. Then if you can shift it, this function, wavelet function will go here. So this tau will change its time axis. Okay. And then again you change its scale. You suppose one scale s1, then you change its scale, so psi of t minus tau by s2. So depending upon s, this wavelet, it may be either compressed or it may be stretched. Okay. So as you increase this scale s, you are basically decreasing the frequency. Okay. So what you are doing in the wavelet, continuous wavelet transform, you are basically now getting a time scale plan, tau and s. Okay. So you will get different coefficients here. For a particular value of tau and for a particular value of s, you will get some value here. Okay. Suppose this is s1, then s2, s3, s4, and you're changing at tau. And it is not necessary that this s, it must be a discrete value, it can be any value, it is continuous wavelet transform. Okay. So for a particular value of tau and for a particular value of s, you will get some value here, x of tau s, which is the continuous wavelet transform. It means what this value gives you. So at this particular value of tau and at this particular value of scale, so if you have a function, you have some signal here f of t. So you have chosen a wavelet which is now located at this time, and its mother wavelet is scaled by this scale, and at this time we are finding the correlation between the wavelet and this function. Okay, so multiplying the wavelet with the function for this time interval. So since the wavelet is of finite duration, so automatically there is a effect of window. So within this window, this function is multiplied with the wavelet and you are integrating it, you are getting some value which is called as continuous wavelet transform. And then you shift this wavelet by some other time, it will go here, suppose at tau 1, and if the scale is same, you will get some other value here. Okay, then you change the scale. So at this scale, your wavelet may be compressed, it will become more narrow. So at this time and at this scale, you are getting another correlation value and so on. So you have time scale plan, a time scale grid basically. Okay. So for a particular value of translation tau naught and for a particular value of the scale s naught, you are getting a correlation between the signal and the wavelet. Okay, now this is very much similar to the Fourier transform. That okay, in the Fourier transform, what you say that the frequency which matches with the signal at that point, you get a high value of this coefficient x omega naught. We have a spectrum like this, maybe. It means corresponding to these frequencies, omega 0, omega 1, omega 2. These frequencies, they are basically most, you can say exactly, they are matched with the signal, or they are present in the signal. This is how we get the frequency information. And the wavelet transform, you say that at which time and at which frequency or which scale the signal is matched to the wavelet. Okay, that is obtained where you get the high values of these coefficients. Okay, so you multiply a signal with the wavelet and you integrate it, you get some value which is the continuous wavelet transform. So if that value is high, it means at that time that frequency is present. This is how you analyze the signal simultaneously in time and frequency. So get time and the frequency information simultaneously using the wavelet analysis, because by shifting the wavelet you are getting the time information, and by changing the scale you are getting the frequency information. Okay, so wavelets, they are basically, so continuous wavelet transform is another way how you define the wavelet transform if you assume that the translation and the scale parameters, they are continuous. Okay, so this is very much similar to your Fourier transform, which finds the degree of correlation or the similarity between the signal and a wavelet at a particular point of time. Okay, so this is all about this, and we use continuous wavelet transform basically for time frequency analysis. But when you use discrete wavelet transform, which is the most widely used transform, DWT, because it has many uh, features that we already discussed, that why DWT is effective, and more you can say, if you see the DWT, we will see in the later lectures that DWT basically the coefficients, the DWT coefficients, which are the expansion set coefficients, they can be computed very easily using a filter structure which is called as a filter bank. Okay, so the lower resolution coefficients, they can be computed from the high resolution coefficients using a filter bank. So you have tree like structure. So if you pass a signal through a low pass and a high pass filter, you call these as detailed coefficients, and these are approximation coefficients. Then you again pass it using the same filters, low pass and high pass, and so on. So this simply becomes a discrete wavelet transform. Its implementation is very efficient and very simple. Okay, and DWT in the wavelets, again I will just revise it, that why wavelets are effective, because a function in the wavelet DWT domain, it can be represented by this series of coefficients AJK. Okay, and you have some other wavelet. So this function is decomposed in the form of a two-parameter system series like this. Okay, so this AJK, this is my discrete wavelet transform for this function f of t. So wavelets, they are adaptive in nature. It is not like the Fourier analysis that okay, once you choose, or once you have decided to choose the Fourier transform or the Fourier series, your basis functions are fixed. You have only choice, that is sine and cosines, nothing else. But in the wavelets, you have many choices, or even there is a provision that you can design your own wavelet for a particular signal. Okay. So wavelets, these coefficients A, J, K, they are, for most of the signals, their dimensions or their values are zeros for most class of signals. So as a result, this transform is highly useful for data compression and signal denoising. Okay, that is important application of this DWT and we have just seen that you can implement this discrete wavelet transform using filter banks, which is very efficient and a simple way to implement DWT on any digital computer. Okay, so with these properties of the wavelets, we will next study a very important topic related to the wavelets, which is called as multi-resolution analysis. And there we will see that, okay, apart from the wavelets, we sometimes need another function which is called as scaling function. In fact, for most of the wavelets, we first design a scaling function, and then the wavelet function psi t, it is basically generated from the scaling functions. Okay, and by using these two functions, any class of signals, I mean most of the signals which are in this domain L-scara, that is the domain of square integrable functions, they can be represented by wavelets and scaling functions. Okay, and then after that we will see that, okay, how this discrete wavelet transform, or how these coefficients they can be computed using this filter bank structure. Okay.